Magis Day viewers, I am Craig Bimangaser.
I am Auditor M. Lacaste, and we are from BSEC 3.
Today, we will dive into mathematics and signal processing because we will learn about Z-transform. But before defining and discussing what Z-transform is, we need first to track back and recall the difference between continuous and discrete time signals on the grounds that these are essential concepts that will lead us to fully grasp what Z-transform is. So, we remember that when we talk about continuous time signal, the time is continuous. Continuous time signal can be defined for all values of time. Here, the independent variable is time and denoted with t. Here is the graphical representation of a continuous time signal. On the other hand, discrete time signal obviously tells us that the time is discrete. Discrete signals are defined for only at discrete time. Here, the independent variable is time and denoted with n. Below is a graphical representation of a discrete time signal. We also recall the concept of continuous and discrete time Fourier transform, wherein we know from our previous lesson before that the continuous time Fourier transform deals with continuous time signal. It is used for transforming the continuous time domain signals into the frequency domain signals. Continuous time Fourier transform exists for energy and power signals. We have this formula for continuous time Fourier transform, which is x of omega equal to x of t, which is our continuous time signal, times e raised to the negative j omega t dt, evaluated from the negative infinity to the positive infinity. Now, we move forward to remembering Laplace transform. We realize that Laplace transform is just a general case of the continuous time Fourier transform, which I just recently discussed earlier. Laplace transform exists in energy, power, neither energy nor power signal. On the other hand, a discrete time Fourier transform deals of course with discrete time signals. It is used for transforming the discrete time domain signals into the frequency domain signals. Discrete time Fourier transform, the same with continuous time Fourier transform, also exists for energy and power signals. We remember that in Laplace transform, we use x of s is equals to x of t times e raised to the negative st dt evaluated from t is equals to the negative infinity to positive infinity. If we have Laplace transform, which is the generalization of continuous time Fourier transform, we also have the Z transform as its counterpart, since Z transform is the general case of discrete time Fourier transform. Z transform also exists in energy, power, neither energy nor power signals. Z transform is represented by the formula x of z is equals to the summation from n equal to negative infinity to positive infinity with a discrete time signal x of n times z raised to the negative n. Now, if we just analyze the formulas we have presented to you earlier, we can actually identify the relationship among those. Laplace transform has this formula shown in the upper left of the screen, and we have the formula for continuous time Fourier transform in the lower left. If we try to observe, these two formulas are somehow of the same form, and it's just a matter of having the similar variables which separates them from each other. But if we let s is equals to r plus j times omega, and r is equals to 0, and s is equals to j times omega, we will come to realize that if we substitute it to our Fourier formula for continuous time Fourier transform, we will end up having the formula x of s is equals to x of t times e raised to the negative st dt, evaluated from t is equals to negative infinity to positive infinity, which is the formula for Laplace transform. Now, we analyze the Z transform where its formula is in the upper right as you can see. And we have the formula of discrete time Fourier transform in the lower right. These two formulas are also somehow in the same form but with different variables used. We focus our attention to the discrete time Fourier transform, wherein if we will let z is equals to r e raised to j omega and r is equals to 1, expectedly, we will also arrive having the formula of z transform if we try to substitute and alter the variables. From this analyzation, we can conclude that Laplace transform is just equal to continuous time Fourier transform, and the same idea applies to the other party. Z transform is just equal to the discrete time Fourier transform. We just have to be mindful that continuous time Fourier transform and discrete time Fourier transform are just the general case of the Laplace and Z transform, respectively. Finally, after all the things we have recalled, we are now down to focusing and defining our main topic for today, which is really the Z transform. Z transform is a major mathematical tool for analysis in such topics as digital control and digital signal processing. The Z transform is a function of a complex variable. The transform itself can also take on complex values. As a result, it is a complex function of a complex variable. The Z transform of a discrete time signal, x of n, is defined as the power series. In this case, we want to calculate the corresponding Z transform of the signal x of n. X of z is equals to the summation of from n equal to the negative infinity to positive infinity with the discrete time signal x of n times z raised to the negative n, wherein we need to be mindful that z is just equals to r times e raised to negative j omega. And remember that the z is a complex variable. N in the formula is an integer and r is our magnitude. Omega is a complex argument. So we have here x of z is equals to x sub 0 of n plus x sub 1 of n times z raised to negative 1 plus x sub 2 of n times z raised to negative 2 and so on and so on. Is just equals to the summation from n equal to negative infinity to positive infinity with the discrete time signal of x of n times z raised to the negative n. This whole thing is just showing us how the summation process within the z transform of a signal. Since we have a polar form involved in the formula, we have here a polar plot.
Now, I'm going to discuss the types of Z transform. There are two types. The first version of Z transform is the bilateral or two-sided Z transform. In some sources, it is also known for bidirectional Z transform. The bilateral or bidirectional or two-sided Z transform of a sequence is defined mathematically as x of z is equal to the summation from n equal to negative infinity to positive infinity x of n times z raised to negative n. Here, z is a complex variable and the set of values of z for which is the sum. By first considering the bilateral or two-sided version of z transform, when we are performing the summation, we used to take the summation index from n equal to negative infinity to positive infinity. That means that it covers both region from negative infinity to 0, then 0 to positive infinity, or both positive and negative region. The bilateral or two-sided Z transform is very useful in dealing with all signals, whether it is causal, non-causal, or two-sided. The second version of Z transform is the unilateral Z transform. The unilateral Z transform of a sequence is defined mathematically as x of z equal to the summation from n equal to 0 to positive infinity x of n multiplied to z raised to negative n. Unilateral Z transform differs from the bilateral Z transform because the summation is carried out only over non-negative values of n. It means that we used to take the summation index varies from 0 to positive infinity only. Unlike in the bilateral, we consider values of n from positive to negative infinity. The unilateral or one-sided Z transform is very useful because we mostly deal with causal sequences. Also, it is mainly suited for solving difference equations with initial conditions. So that's the main concept when we are dealing with unilateral Z transform. Before I'm going to discuss the properties of ROC, let us first define what does ROC means. The ROC stands for region of convergence. It means that x of z is set for all the values of z for which x of z attains a finite value. Always remember that every time when we are solving for z transform, we must indicate its ROC. What is the significance of ROC? ROC will decide whether a system is stable or unstable. ROC also determine the type of sequence, whether it is causal or non-causal, finite or infinite. Properties of region of convergence. The first property is that the ROC is consists of a ring in the z-plane centered about the origin. As we can see in the figure shows the z-plane. The horizontal axis is the real part and the vertical axis is the imaginary part. And the z-plane is consists of a ring or a disk that's centered about the origin. We should also consider for the first property, convergence is dependent only on R, not on omega. In some cases, the inner boundary can extend inward to the origin. In other cases, the outer boundary can extend outward to infinity. The second property states that the ROC does not contain any poles. By definition, a pole is where x of z is infinite. Since x of z must be finite for all z for convergence, therefore, we can say that ROC does not contain any poles. Next property states that the ROC of a linear time invariant stable system contain unit circle. In the Z-transform domain, the necessary and sufficient condition for a LTI or linear time invariant system to be stable is that its ROC should contain the unit circle. Next property states that the ROC must be a connected region. This property is useful for evaluating the existence of Z-transform when x of n is a sum of two sequences, one left-sided and the other is a right-sided. Next property we have finite duration sequence. For letter A, it states that if x of n is causal, the ROC is entire z-plane except at z is equal to 0. As we can see in the figure, it shows the graphical representation for finite duration, right-sided signal. And when we look at the z-plane, the shaded part is what we call the ROC. There, we can see that the entire z-plane is shaded except in the origin. One example for this property is the unit sample sequence. So if we evaluate this function, the unit sample sequence has a z-transform equal to 1. Since it exists for all values of z, hence the z-transform converges for all values of z. Thus, the ROC of a unit sample sequence is the entire z-plane. For the letter B, it states that if x of n is non-causal, the ROC is entire z-plane, except at z equal to infinity. As we can see in the figure, it shows the graphical representation for finite duration left-sided signal. And when we look at the z-plane, the shaded part is what we call the ROC. There, we can see that the entire z-plane is shaded except at z equal to infinity. For the letter C, it states that if x of n is two-sided sequence, the ROC is entire z-plane except at z equal to 0 and z equal to infinity. Simply, we can conclude that it is just the combination of letter A and B. As we can see in the figure, it's shown there a graphical representation for the finite two-sided signal. Moreover, looking on the z-plane, we can conclude that entire z-plane was shaded except at z equal to 0 and z equal to infinity. Last property, we have an infinite duration sequence. For letter A, it states that if x of n is causal or right-sided sequence, the ROC converges for mod of z greater than r sub 2. If we look at the z-plane, it shows the ROC or the shaded part is found in the region outside the outermost pole. In other words, it can be seen in the exterior of the circle equal to the largest magnitude of the pole of x of z. Note that the pole is not included in the ROC since the z transform does not converge at a pole. One example for this property is the unit step signal. As we all know, the unit step signal does not exist for negative time. Thus, the signal is causal or right-sided signal because x of n equal to 0 for n less than 0. Therefore, the ROC of the unit step signal is located in the outermost of the circle. For letter B, it states that if x of n is non-causal or left-sided signal, the ROC converges for mode of z less than r sub 1. Again, by looking at the z-plane, the shaded part is the region of convergence that is located inside the innermost of the pole. In other words, it is located inside the circle of the radius, equal to the smallest magnitude of the pole of x of z. And then, for letter C, the property states that if x of n is two-sided signal, the ROC converges for mod of z is greater than r sub 2 but less than r sub 1. It only means that the ROC is the ring in the z-plane bounded on the interior and the exterior by poles. To further understand the z-transform, we provided one example. In this example, we are asked to solve for the z-transform and the ROC. As we can see, the given example is a unit step signal. As we all know, the unit step signal or step function is the type of standard signal which exists only for positive time, and it is 0 for negative time. In other words, a signal x of n is said to be step signal if and only if it exists for n greater than or equal to 0 and 0 for n less than 0. As we all know, the formula for z-transform is defined mathematically as x of z is equal to the summation from n equal to negative infinity to positive infinity x of n times z raised to negative n. Now, we need to find out the z-transform of the discrete unit step signal. So here, we are considering in place of the unit signal x of n, we just replace it by u of n. So the form now is x of z equal to the summation from n equal to 0 to positive infinity u of n z raised to negative n. Now, we know that this is a standard unit step signal. Thus, we need to change the range and this will lie from 0 to positive infinity. Simplifying, we get this equation. X of z is equal to the summation from n equal to 0 to positive infinity z raised to negative n. To get rid of the negative exponent, we simplify the equation in this form. X of z is equal to the summation from n equal to 0 to positive infinity quantity z raised to negative 1 raised to n. And this equation is equivalent to 1 plus z raised to negative 1 plus z raised to negative 2 plus z raised to negative 3 plus so on and so forth. As we can see here, we can relate this form to the infinite series of a geometric series with a constant or common ratio of z raised to negative 1. Note that the equivalent geometric series for this one will just be the summation from n equal to 0 to negative infinity x raised to n is just equal to 1 over 1 minus x. We treat the z raised to negative 1 as x, then we can now write the whole expression in 1 over 1 minus z raised to negative 1, provided that mod of z raised to negative 1 is less than 1. Simplifying, we get z raised to negative 1 can be written as 1 over z raised to negative 1. Simplifying, we get 1 over 1 minus 1 over z. Then, finally, we can read the z transform of standard discrete unit step signal in this form. X of z is just equal to z over z minus 1. After deriving the unit step signal to z transform, the next thing that we must do is to solve for the region of convergence. In solving the ROC, we must consider the condition that we use in applying the geometric series. The condition states that the mod of the constant ratio should be less than 1. To get the condition for the mod of z, we can write this as mod of z is greater than 1. The restriction that this result is only valid if z raised to negative 1 is less than 1, or equivalently, mod of z is greater than 1 means that the position of the complex quantity z must lie outside the circle, center, origin. And that's all for today's topic, which is z transform. See you next time on another fun exploration in the world of digital signal processing. Again, I am Alzater M. Lacaste.
And I am Craig B. Mangasser. Thanks for watching!